So in the last section, we tested to see if data followed a distribution. That was the first type of chi-square test called a goodness of fit test. Now we want to do what's called a test of independence or a test of association between two qualitative variables. So this is also called a two-way contingency table. And let's look at an example here. So we want to test if marital status is related, so associated. So this is a test of association. With a person's state of happiness at the alpha equals 0.05 level. And here's our survey data. So marital status, married, unmarried, and then they respond whether they were happy or unhappy. We can see of the married, more people are happy than unhappy. Of the unmarried, we can see more people are unhappy than happy. But is it statistically significant? So our null hypothesis is going to be that there's no relationship. So it's going to be marital status and happiness are independent or not related, not associated. And then HA, the alternative hypothesis, is going to be that they are dependent or they are related, they are associated. So we need to form what's called an expected contingency table, and this contains the expected counts of the different cells. So these are what we observed, the observed counts, 4 observed counts, and then we had row totals and column totals. Now we want to look at expected counts. So the definition of expected count is you take the sample size, multiply by the probability in row I times the probability in column J. So your probability is going to be desired out of totals. So you would do your row total divide by n, and then times your column total divide by n. But notice here that one of those n's will cancel out top to bottom, so we can just do row total times column total on the top, divide by your grand total n, in this case 158 on the bottom. So that's how we find expected counts. And what we want to do is see if there is a statistically significant difference between our observed counts and our expected counts. And let's go ahead and compute some of those expected counts. So the expected count here for married happy, you're going to do the row total 102 times the column total 79 and divide by 158. So let's go ahead and do that real quick. So 102 times 79 divide by 158, so 51. And do the same thing here for married unhappy. So 102 times 79 divided by 158. That will also be 51. Same numbers. And then here, happy unmarried. 79 is your row total. I'm sorry, your column total. 56 your row total. Divide by 158. So 79 times 56 divided by 158. 28. And then the same 28 here. 79 times 56 divided by 158. So those are the expected counts, E sub I. So here are our observed counts, here are our expected counts. They both add up to 168. Now our test statistic, I should mention test requirement, all your cell counts have to be at least 5. All of ours are at least 5. So our test statistic is the same as it was with the goodness of fit test. You do observed minus expected, square it, and then divide by expected. So square it to get a positive measure, divide by expected to get a relative measure, and then sum those up. So I've done that in this table here. So here's observed counts, expected counts, and then I did observed minus expected, so just subtract your columns. So 55 minus 51, 4. And then observed minus expected squared. So square the 4, you get 16. And then observed minus expected squared divided by expected. So take that 16 and divide it by the 51. And if you do that, you will get 0.3137. And I went ahead and filled in the other 3 rows of the table for you. Now if you tally up these totals here, observed minus expected totals to 0, that should always happen. And that's why we square things, because if we didn't, if this square was not there, then our chi-squared would just be 0. So 4 times 16, that is 64. And then if you sum up these, you get approximately 1.77. So that is our test statistic. And then the decision rule for this test of association, your degrees of freedom, you take rows minus 1 times column minus 1. So we had 2 rows and 2 columns in our expected and observed tables, not including the totals. So this would be 2 minus 1, 2 minus 1. So that's 1 times 1, which is 1. So that's our degrees of freedom. We're testing at the 0.5 level, so our critical value is chi-squared 0.05. So let's go ahead and find that with the distribution calculator. So here, degrees of freedom 1, 0.05 is our alpha, 3.84. And so your decision rule, you're going to reject x0 if your chi-squared is greater than 3.84. Okay, our conclusion, well, chi-squared, which is 1.77, is actually less than 3.84, which is our critical value. So we do not reject H0. So remember, H0 was that marital status and happiness are independent, and marital status and happiness dependent was HA. So we cannot conclude HA, not sufficient evidence to conclude that they're dependent. So conclusion, there is not sufficient evidence to conclude marital status, and happiness are dependent or related. So we would conclude the null hypothesis that they are not related. So based on that, here is the general form of a two-way contingency table analysis, or test of independence there. So our test requirements are that the n observed counts are a random sample from our population of interest. This is considered a multinomial experiment with R times C, rows times columns, possible outcomes. Your sample size n has to be big enough so that the expected counts are at least 5. Your null hypothesis is always that the characteristics are independent, your alternative that they're dependent, and your expected counts are going to be row total times column total divided by grand total. Test statistic is the same as it was for goodness of fit, observed minus expected squared over expected, sum that up, and your decision rule is the same as it was for goodness of fit. Your chi-squared test statistic has to be greater than the critical value. It is always a right-tailed test, and your degrees of freedom are rows minus 1 times columns minus 1.